Welcome to Online Algebra 2 class. Today we are going to cover section 8-3, rational functions and their graphs. So our objective for this section is to identify the properties of rational functions and to finally graph rational functions. What you need to know is that if a function has a polynomial in its numerator or its denominator and the graph has a gap at each zero of the polynomial, the gap could be a 1-point hole in the graph, or it could be the location of a vertical asymptote. All right, so before we get into this a little bit, let's try to talk about what exactly a rational function is. And a rational function is a function that you can write in the form of a function is equal to some polynomial over another polynomial, where p of x and q of x are both polynomial functions, and the domain is always going to be all real numbers except for the things that make the denominator equal to 0, because you can't have a 0 in the denominator. Okay, so think about what exactly this means. This means we're going to have some sort of function, and it's going to have some stuff on the top, it's going to have some stuff on the bottom, and whatever the stuff on the bottom is can never be equal to 0, or else the function is going to be undefined. And that's going to make the graph do some strange things. All right, so these are three examples of rational functions and what they look like. We have a polynomial on the top, x squared, and then we have a polynomial on the bottom, x squared plus 1. Well, it's not actually possible to make x squared plus 1 equal to 0 using real numbers, because if we set it equal to 0 and try to solve, taking the square root of both sides, we get that x is equal to plus or minus I. Well, since that is not anywhere on the real number graph, the only number that we can plug into x to make it equal to 0, to make the denominator equal to 0, would be I. So if you look at this graph, it doesn't have any weird stuff. It doesn't have any places where it's not defined. However, in the second function, we could plug in -2, and this function would be undefined. That's why there's this break in the function, this hole in the function. And we're going to talk about the difference between, this is called a discontinuity. We're going to talk about the difference between this type of discontinuity and this one, right? If we plug in 2 to this function, the function is not defined at 2, and this graph goes by 2's. So you can see that there's this line up and down that the graph never crosses, called a vertical asymptote. Okay, so this is one type of discontinuity. This is a different. This function, this rational function, doesn't have one because it's not possible to make the denominator equal to 0. And in each case, all I'm doing is saying, where is this true? Set the denominator equal to 0 and see where, if anywhere, the function is actually undefined. And this first one, right, x squared over x squared plus 1, there's no value that makes the denominator 0, so it is called a continuous graph because it has no jumps, no breaks, or no holes. The other two are called discontinuous graphs because this one you can draw without picking up your pencil. This one, right, has a hole. This one is very clearly not able to connect these 2 points. Okay, and again, these have special names that we'll get into in a few minutes. Okay, so if, and these are now called my points of discontinuities. So if a is a real number for which the denominator of the rational function is 0, okay, so it's something that makes the denominator 0, then that means that a is not in the domain of my function. The graph of f of x is not continuous at this point because it made the denominator equal to 0, and that means we have a point of discontinuity. Now there's 2 types, removable and non-removable. This graph, the one with the hole, if you notice something, these two can cancel. Okay. So, right, these two cancel. It has a removable discontinuity. The hole in the graph is called removable because you can make the function continuous by redefining it at x minus 2 so that f of negative 2 is equal to 1. So basically what this is saying is that you can cancel out this thing and make the new function x plus 3, right? And then if I plug in negative 2, I would get 1. So if you put a point here, this function would be continuous. So you were able to remove the discontinuity by canceling it. It is called a hole in the function. However, the other one, x plus 4 over x minus 2, can't cancel anything. It has a non-removable discontinuity, also called a vertical asymptote. Okay? Notice this line goes vertically up and down. This is called a horizontal asymptote. We'll talk about that in a few minutes. But this line goes up and down, and the graph never crosses it. So this graph, continuous. This one has a removable discontinuity, also called a hole in the function. This one has a non-removable discontinuity, also called a vertical asymptote. Okay? Or also called an infinite discontinuity, because this side and this side both go straight up and down to infinity. Okay. When you're looking for discontinuities, the best thing to do is factor. Okay? So when you're factoring, it's a lot easier to tell what's going to make the denominator equal to 0. Right? Everything that those different factors. Okay? So the factors of the denominator will reveal the points of discontinuity. If the discontinuity is called by this factor to some power in the denominator, it could be removable if you have that factor in the numerator. All right, let's try one of these. Okay. What are the domain and points of discontinuity for each rational function? Are they removable or non-removable? What are the x and y intercepts? Okay, so let's see how you could go about looking at this function. This is a rational function. It's got x's in the top, x's in the bottom. It's a function it's a function in the top and a function in the bottom. The best way to start this is to factor it. So x plus 3 doesn't factor in the top, but the bottom factors, it factors into x minus 3, x minus 1. Okay, so now just by looking at this, I can tell a few things. The domain and points of discontinuity. The domain of this function, the domain of any function is, any rational function is all real numbers except for the stuff that makes the denominator equal to 0. So the domain of this is going to be that x is not equal to anything that makes the denominator equal to 0. So that's going to be 3 and 1. Okay? If I want to write that in interval notation, this function goes from negative infinity to 1, then from 1 to 3, and then from 3 to positive infinity. There's only two places where this function is not defined, 1 and 3. Okay? These are the 2 points of discontinuity. Are they removable or non-removable? Well, nothing cancels, so that means they're non-removable. That means these two are both vertical asymptotes. And we'll get to what that looks like on a graph in a little bit. What is the x-intercept? What is the y-intercept? Well, if you want to find the x-intercept, right, just like this is true, if there's a 0 in the denominator, this function is undefined. No matter what the bottom is, if there's a 0 in the numerator, this answer is equal to 0. Okay, so if I want to find the y-intercept, or the intercepts, if I want to find the x-intercept, all I have to do is set the top, the numerator, equal to 0 now. So x plus 3, set that equal to 0. All right, and we get that x is equal to, whoops, negative 3. Okay, so the x-intercept is -3. Okay, the y-intercept we get by plugging in 0 for x. So we would just go like this, over 0 minus 3 times 0 minus 1, which would be 3 over 3, which would be 1. So now we got a couple points here, right? We have that x was 0, y is 1. We have that x is -3, y is 0. And we have two vertical asymptotes. So we're at a good spot to start thinking about what the graph is going to look like, but we'll do that at the end. Okay. So the point of this is to look at the problem and figure out all this stuff about this rational expression. Let's try this one. Oops, I'll get to that one in a second. This one. Okay. Factor the denominator. I don't really see how it factors. If I set the denominator equal to 0, we can see that it's continuous. So the domain of this function is all real numbers. All right, so that means it has no points of discontinuity because there's nowhere that the bottom is equal to 0. I can set the top equal to 0 to give me my x-intercept. And I can plug in 0 to get my y-intercept. So this is -5 over 1, which is -5. And those are some good points to start with for this function. This one. Factor the top, factor the bottom. That'll help me see the points of discontinuity. So factoring the top would give me x minus 4 times x plus 1 over x minus 4. So that means that x, the domain, is all real numbers except x cannot be equal to 4. But look carefully. These two, x still can't be equal to 4, but these two can cancel. So when I do that, this function then just becomes x plus 1, and I've removed this discontinuity. So that means that this is a hole in the function. Okay. There is one little spot where this function has a little break. It looks like it could be continuous. It looks like it's going to be a line, except at 4. There's a hole in the function. All right, well, I know at 4 there's a hole in the function, but this also has an x-intercept of -1 and y-intercept of a positive 1. And this would be pretty easy to graph, right? So y-intercept, slope-intercept form, it's just a line, except instead of looking like a line, it would look exactly like a line, but there would be a hole in this function. Okay? Let's try a couple more kind of problems. All right. So for the first one, I would factor the bottom. So that's x plus 4, x minus 4. All right. That means that x cannot be equal to plus or minus 4. Both of these are vertical asymptotes. They're non-renewable discontinuities. Okay. And x-intercept and y-intercept, this has, right, you can't set the numerator equal to 0. It's always going to be 1. So this has no x-intercept. And to find the y-intercept, it would be y is equal to -1 over 16. You would just plug 0 into this function. Okay. All right, we would just go like this. 0 squared minus 16 is -1 over 16. For the next one, factor the top, factor the bottom. The bottom does not factor. The top does factor. still factor it because now I can see a few things, right? The domain is all real numbers because the only way to make the denominator equal to 0 is with imaginary numbers. X is going to be equal to plus or minus 1, right? This function will cross the x-axis at -1 and at +1 because that's what makes the numerator equal to 0. Who cares what the denominator is? If the numerator of a fraction is 0, when you divide them, you're going to get 0. And when we plug in y to get my y-intercept, we would get -1/3. Okay. For the last one, factor it. So y is going to be x plus 1 over, bet something's going to cancel here. Yep, x plus 1, x plus 2. Okay, that means that x, the domain, is that x cannot be equal to -1 and -2, but this is a hole, this is a vertical asymptote. This discontinuity is removable, this one is non-removable. And let's, this at -1 is a hole in the function, so it can't be an intercept and a hole, it's a place where the function is not defined. So this function has no x-intercept, and the y-intercept, right, just plugging in 0 would be 1/2. All right, so in chapter 7, we learned that an asymptote is a line that the graph approaches. If a rational function has a non-removable discontinuity, it is a vertical asymptote. So we've already mentioned that, we already covered that. Okay, so the graph of a rational function has a vertical asymptote at each real 0 of the denominator as long as nothing cancels. If it cancels, it's a hole. Okay. So what are the vertical asymptotes here? This is already factored for me. That's nice. I don't have to factor. Nothing cancels. So my vertical asymptotes are going to be x is equal to 2 and x is equal to 3. Okay. The two places that this function is not defined, the two places where the denominator is equal to 0. If we want to do all the stuff we did before, right, this function would have a x-intercept. The domain would be all real numbers except for these two. It would have an x-intercept of -1 because that's where the numerator is equal to 0. And I could plug in y to get my y-intercepts, which looks like +1/6. So let's run through all these real quick. They're all factored for us, so that makes it easy. The vertical asymptote, the vertical asymptotes here is x equals 1 and x equals -3 because nothing cancels. For here, the vertical asymptote is only x is equal to -3. There is a hole in the function at 2 because these two can cancel. So there is a difference in the graph. So you need to be able to recognize what is a vertical asymptote and what is a hole in the function. This is not factored, so make sure you factor it. So that's x plus 1, x minus 1, x plus 1. Those two cancel. That means that there is a hole at x is equal to -1. All right. So the graph can have more than one vertical asymptote. This one had 2. Okay. So while the graph can have any number of vertical asymptotes, it cannot have more than one horizontal asymptote. And there's some tricks to figuring out if the graph has a horizontal asymptote and where it is. So to find the horizontal asymptote of a graph of a rational function, we are going to compare the degree. of the numerator to the degree of the denominator. Okay, so we're looking at the exponent. We're looking for the biggest exponent. So instead of factoring, this one you can start with right away because it's a little bit easier to tell the horizontal asymptote in the unfactored form versus the factored form. Okay? If the degree of the numerator is smaller than the denominator, the graph has a horizontal asymptote at the x-axis at y is equal to 0. If the numerator's degree is bigger, it does not have a horizontal asymptote. It does have a different type, called a slant asymptote if the degree is 1 bigger, a quadratic asymptote if the degree is 2 bigger, a cubic asymptote if it's 3 bigger, and so on and so on and so on. But we're not going to deal with that in this course. So for now, we're just going to say it doesn't have a horizontal one. It could have a different type of asymptote, right? But it's just not going to be horizontal. If the two degrees are even, okay, then you have to do one more thing here. Then you have to look at the leading coefficient of the numerator and the leading coefficient of the denominator, and you divide the two, and that's where the horizontal asymptote is. Okay, so numerator bigger, none. Denominator bigger, 0. The same, divide the leading coefficients by each other, right? And unfortunately, this is something you're going to have to practice a little bit and just try to remember. All right, so what is the horizontal asymptote for this, for these functions, okay? So look at the first one here. Notice that the degree of the numerator is 1, the degree of the denominator is 1. So that means they're the same. So that means that the horizontal asymptote is going to be this over this. And we can say y is equal to 2. Right? The horizontal asymptote, 2 over 1. Okay? This function, if we want to go through, the question doesn't ask us for more than this, but this also has a vertical asymptote at x is equal to 3. It has an x-intercept of 0, right? If I set this equal to 0, and it would have a y-intercept of 0 as well, right? Plug in 0 for x, you would get 0 over -3, which is 0, right? So the question didn't ask us for these three, right? But we're sort of just building all the information possible about this rational function in order to get to the last problem where we try to graph it. All right, so first, you don't need to factor it. In fact, it's better to just leave it here and just look for the horizontal asymptote before you factor. The horizontal asymptote here, well, the bottom is bigger degree, is 0. Okay. Now, if you wanted to find the vertical asymptotes, then you would have to factor, see if anything canceled, and do more. But to just answer this question about the horizontal asymptote, we leave it in its unfactored form. And here, for this problem, the numerator is bigger, so horizontal asymptote, there is none. So if the numerator is bigger, if the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Let's run through those again real quick. Here, they're the same, degree is the same, so the horizontal asymptote is y is equal to -2 over 1. Degree of the denominator is bigger, so the horizontal asymptote is 0. Numerator is bigger, so the horizontal asymptote is none. Okay, all we're doing is looking at the exponents. Okay, now let's graph these. And we can get a reasonable graph, and these are going to be estimations, right? Our graphs don't have to be perfect, but we're going to take all the information that we can get from these functions, and we're going to use it to make the graph. So we can get a reasonable graph for a rational function by finding all the intercepts and all the asymptotes and plug in some few extra points to get an idea of the shape and use the asymptotes to help you. Okay, so first, here's my function. Let's factor it. So we got factors of 12 that subtract and give you 1. So that's x plus 4, x minus 3 over x squared minus 4 is x plus 2, x minus 2. Okay, well, nothing cancels. Okay, that makes the vertical asymptote at x is equal to negative 2 and x is equal to positive 2. Horizontal asymptote. I go back to the original function and I see that the degrees are the same, so that means y is equal to 0. So what you want to do to start graphing these things is draw those asymptotes. The vertical asymptotes go up and down. So we have one at negative 2, and we draw them with dotted lines, and at positive 2, drawn with a dotted line. The horizontal asymptote at 0, and basically what this means, it means graphs never cross a vertical asymptote because they are places where the function is not defined. But a graph could cross a horizontal asymptote. It just means a horizontal asymptote means the ends of the function. As we go left and right, it's going to be getting really, really close to this line. So what happens in the middle, we don't know. All right, but let's get some points here. So x-intercept, it's everywhere the numerator is equal to 0. So that's negative 4 and positive 3. Let's put a, oh, I made a mistake here. They're the same, right? These two are the same, same degree, so the horizontal asymptote is 1. Sorry about that. Okay. I got to remember the rules for horizontal asymptotes, right? And that didn't make sense because I had 2 x-intercepts on a horizontal asymptote. I knew I did a quick little mistake. All right, so negative 4. So that's going to be a point on this function. And 3. That's going to be on point on this function. So it's not symmetric, right? We can't assume that both sides are going to be the same because they're clearly not already, right? But they're going to look kind of the same. Let's get the y-intercept. Okay, so y-intercept, I'm going to plug 0 into this function. 0 squared, 0, 0 there. We get negative 12 over negative 4, which is 3. So 1, 2, 3. So there are some points. Is that enough points to graph this function? Not really. So now what you're going to do is you're going to make a table to get the rest of these points, right? We're going to get more points. You want to try to get some points close to the asymptotes, okay? So you don't have to go crazy like with graphing fractional points, but we want to sort of pick every integer to sort of get an idea of what this function looks like. So that means I'm going to plug in 1. Can't plug in 2. It's an asymptote. I already have 3, so I'm probably going to plug in 4. And let's see if that's enough to graph just this right-hand side. And then on the left, I'm going to plug in negative 1 because that'll finish off this middle section. And I'm going to plug in negative 3, and let's see if that's enough to finish off the right. Okay, so you can plug it into either the factored form or the original form. It doesn't really matter. Let's just plug 1 into the original function right here. And we get 1, 1, minus 12, so that's going to be negative 10 over negative 3, so that's negative or positive 10 over 3, which is 3 and a third. So that's 3 and a third right there. Okay, these graphs do not have to be exact. Okay, let's jump right to negative 1. So if I plug in negative 1, Negative 1 squared is 1. Minus 1, so that's negative 12. Negative 1 squared is 1. Minus 4, that's negative 3. So my answer here would be 4. So, again, not symmetric. So just because you have a point here, it doesn't mean it's going to be over there. But those 3 points are enough to graph this function. Because we know that the function either has to be going straight up or straight down as we get closer to the vertical asymptotes. And I can see it's kind of going to curve like this. Okay, let's plug in my other points. If I plug in a 4, I'm going to get 2/3. So 4, 2/3, kind of like that. That's pretty much enough to get the shape of this right-hand side, right? Because if I know that as I get closer and closer to the vertical asymptote, the function is going to be going straight up or straight down, and as I go to the right, it's going to get very close to the horizontal asymptote. So we're going to get something that looks like that. And we're probably going to get the same thing over here. Just to be sure, let's plug in negative 3, and we get negative 6/5, which is a little bit less than 1. So we get something like that. Okay, so this one curves a little faster, but it still winds up looking the same thing. And there is my approximation, not perfect, right? My approximation of the graph of this rational function. If you plug it into a graphing calculator, you may or may not get these representations of asymptotes, okay? But what you need to do to graph these on your own is to draw all those asymptotes as a dotted line. Now let's try this again. Okay. Hopefully I won't make a mistake on this one. All right, factor first. So x plus 3 over x minus 5, x minus 1. Vertical asymptote, nothing cancels, is 5 and 1. Horizontal asymptote, because the denominator is bigger than the numerator, now the horizontal asymptote's at 0. Let's put these in. 5, 1, horizontal asymptote at 0. So now that the horizontal asymptote's at 0, right, it's not really going to have an x-intercept. So you'd be looking at this and say, well, it's going to be negative 3. That's not really quite going to work out. So let's get the y-intercept, which is going to be 0, 0, 0, 3/5. All right, so when we plug in 0, we get 3/5. Let's just go with something like that. So now if you're making a table for the rest of these, okay, what do you want to plug in? Well, you want to plug in all the numbers in here. So we're going to plug in 2, 3, 4, 6, 7, and we just plugged in 0, and let's plug in negative 1 as well, right? So obviously there's a lot of stuff to plug in here, and that's why these questions can take a little bit of time to solve. So just take your time, plug in the different points. You can use a graphing calculator if you want, which is what I'm going to do as I pop into Desmos. All right, so what's my function? It is x plus 3 over x squared minus 6x plus 5. All right, so and actually, looking at this, right, x-intercept is -3. Well, you're probably thinking this point's up here, right? -3, how does it cross the x-axis there? It's okay for the graph to cross the x-axis, but what happens is it still gets relatively flat, and it actually crosses maybe, no, actually it doesn't cross there, but it would cross over and just sort of flatten out. So you get something that looked like this, and you see the graph would be going down here. Eventually it would turn and go back up towards this line, but it would be kind of flat out there. Right? So it is okay for the graph to cross the horizontal asymptote. All right, let's get a couple of these points in here. So if we plug in -1, or if we plug in 1, we're going to get 1, 1, minus 6. So it's going to be 4. Oh, -1. 1 is our asymptote. 2 we want to plug in. So let's plug in 2. So that's 5. So that's 4 minus 12 plus 5. And we get -3. So it's 5 over -3. So 1.6. Something like that. So -1.6. 3 would be -1.5. And 4 would be -2 1/3. And I just use a graphing calculator to get these numbers. So 2 1/3. And that's enough right there to graph this approximation of the graph. Right? It's not perfect. It's not going to be exactly what this graph looks like, but it's good enough for what we want to do. Let's finish with 6. And we get 1.8. So 1 point, almost to 2. And 7 gives us, I can't lock in a 7, 0.833. Okay, so 7, boom, right there. And that's enough to get a good approximation of this graph right here. And if you didn't have a graphing calculator, right, you have the function. All you have to do is plug these numbers into it to get a good sense of what this graph actually looks like. All right, last thing is a word problem. This is actually the easier problem. As you work in a pharmacy that mixes different concentrations of saline solutions for its customer, the pharmacy has a supply of 2 concentrations, 0.5% and 2%. They give you the function, which is all you really need to solve this problem. So y is going to be equal to 100 times 0.02, which is 2 plus 0.005x over 100 plus x. The question is, after adding, right, this function does everything for you. So the question is how much must you add for the combined concentration to be 0.9? So all we have to do, 0.9%, plug in what you want. Okay, so you could graph these two things, and when I did that, it didn't really look like it came out very nicely. So much easier just to solve this algebraically. So if you want to isolate x, just multiply both sides by 100 plus x. Right? These two cancel, and we're now left with 0.9. 9 plus 0.009x is equal to 2 plus 0.005x. Right? And now all we have to do is subtract x from both sides, subtract 0.9 from both sides, and we get 0.004x is equal to 0.9. So that's 1.1 divided out, and we get that x is equal to 275. So that means that you should add 275 milliliters of the 0.5 solution to get a 0.9 solution. So not too bad. Again, graphing calculator could get you this answer. Just plug this into a graph and plug in that line, see where they intersect. But I think it's a little bit easier just to solve this algebraically the way it is. All right, so that was 8-3, rational functions and their graphs.